So for our application here, we have that the following data on average sleep and death rates is said to follow a quadratic equation y equals ax squared plus bx plus c. And what we need to do here is find the values for a, b, and c given that data set. So this application is a little bit weird, it's a little bit different, but it does build towards the kind of idea that we're going to be seeing in the next section. So it's a good sort of bridge to get into there. That what we want to do is start from the assumption that y equals ax squared plus bx plus c, and take the values that we have, take these values from our data set that x is 4, 7, and 9 hours of sleep, and y is death rates of 1,682, 626, and 967 males per 100,000. Per 100,000 males? I don't know, it's phrased that clunkily. But point is, we have those as our potential data points. We plug them in. When x is equal to 4, y is 1682. So we would have 1682 equals a times 4 squared plus b times 4 plus c, or 16a plus 4b plus c equals 1682. Then when x is 7 and y is 626, we would have 626 equals 49a plus 7b plus c for fundamentally the same reason. And then at 967, we'll end up with 81a plus 9b plus c equals 967. And we can turn this into a system of equations. We can take all those pieces and condense it down just into that system of a, b, and c, where the fact that this is a, b, and c instead of x, y, and z doesn't actually change anything in terms of our process. It doesn't change anything in terms of the way we look at this. It's just we're using different variable names now. If you want to change those and call them x, y, and z instead because you're more comfortable with that, that works. But I'm going to call them a, b, and c here, for one, because that's the setup we have, and two, because like I said, it'll help us build towards something we're going to see next. So we have that system, and the c seems like the easiest thing to cancel because we've got one c in each of them. So we're just going to end up subtracting a couple of terms. Subtracting the first two from each would leave us with 33a plus 3b equals negative 1056, and 65a plus 5b equals negative 715. Excuse me, I can't talk right now. And then it's probably not super obvious what we want to do from there, but if we divide out a 3 from the first equation, we would get 11a plus b equals negative 352. And if we divide out a 5 from the second, we would have 13a plus b, is equal to negative 143. So we're in another nice case for elimination, which would leave us, after performing that elimination, that is, subtracting one from the other, we would be left with 2a is equal to 209, or more exactingly, a is equal to 104 and a half. So because a is equal to 104 and a half, you can then plug this back in a couple of different ways to be able to get that b is going to be equal to negative 1501.5, where I'm going to leave that to you to check how that goes in there, but you can just plug it back into one of our equations, just like we always have. And then from there, you plug both of these back in. And again, I'm being a little bit brief here because I'm short on space with all of the linear algebra that had to be done up there. You'll get that c would have to be 6,116. So, at the end, if we want to get our model, in terms of that y equals ax squared plus bx plus c, we could call this now a function of x, where this function of x is equal to 104.5 x squared minus 1501.5 x plus 6,016, up to my ability to write the number 6. So if we want to find out what the death rate is per 100,000 males for someone who sleeps 5 hours a night on average, we could plug that in there, and we would end up getting that is approximately, at least according to our model, a value of 1,121 deaths per 100,000. And this is a bit of more an, let's say, abstract application here, at least in terms of the process. A lot of times when we're seeing our applications previously, it's like, hey, here's our model. Now we're going to make this work. We're going to find a special value from the model. In this case, our application is more about being able to set up the model. It's more about the steps to get to it than to actually use it, because using it's pretty straightforward. It's a very chapter 1 type of thing. But this is one way we can use these things in terms of being able to find coefficients that fit a given pattern. And the process of finding coefficients, as I said, leads us very nicely into what we're going to see in our last section for this week, which is called partial fraction decompositions. And that's what we got next.